final talk of our symposium workshop by Felix Leditzky. Felix is at the Perimeter Institute in Waterloo, Canada, and he will be telling us about symmetries and asymptotics of port-based teleportation. Okay.
Thanks a lot, Mark. Thanks a lot for the invitation. I would have loved to come to New York City in person. Yeah, it's great that we can still have this meeting in some form. And I want to tell you about one of my favorite topics in quantum information, which is port-based teleportation. To understand port-based teleportation, we first need to maybe review a little bit what teleportation is, and the fact that teleportation and entanglement are so intimately connected. And Eric mentioned before that, you know, when someone asks you in the street what actually is entanglement, it's a bit hard to give an answer to that. My favorite answer is actually one that the great Charlie Bennett gave. And he said, an entangled state describes the complete knowledge of the whole without knowing the state of any one part. Which in my opinion captures really the essence of entanglement. And it turns out that this concept of entanglement, like knowing the whole state without knowing any one of its parts, means that it's a very strong form of some form of correlation between two systems. And furthermore, like Eric said before, in quantum information, we usually talk about separated systems, and then entanglement provides a certain non-local correlation between those systems. And it turns out that this entanglement, the correlation form of entanglement, is an incredibly useful resource in quantum information processing if you use it together with other resources. And the best and one of the first examples of how to use this in conjunction with another resource was the famous quantum teleportation protocol, which was discovered in 1993 with by the following 6 people. So we have Rita Chosa, Bill Wooters, Charlie Bennett, Gilles Brassard, Claude Crépeau, and Asher Paris. So the original 6 who discovered teleportation in 93. And they realized that the correlation in entangled state can be used together with classical communication to teleport an unknown quantum state. And in my mind, this is kind of the most remarkable effect that we have in quantum information theory, one that is not possible in any classical theory, and one that really relies on this entanglement, this correlation between two separated parties. And I want to talk about a variant of quantum teleportation called port-based teleportation. In order to do that, I will first review some quantum information 101 and maybe 102, so that we're on the same page about the terms that I'm using and the notation. I will then define port-based teleportation by first reviewing the original teleportation protocol and then deviating from this a little bit, which will lead us to port-based teleportation. I will define it and explain some of the properties of port-based teleportation. And then the central thing in the analysis of port-based teleportation are its symmetries. So we'll go through them in fairly a lot of detail. And then I will show how we can use these symmetries to describe port-based teleportation and optimal protocols of port-based teleportation. And then if time is permitting, I will also tell you something about the asymptotics of port-based teleportation. And then I'll close with some concluding remarks. Okay. So quantum systems in quantum information are modeled by Hilbert spaces. For us, it will always be finite dimensional Hilbert spaces. So we have, for example, atoms with a certain number of energy levels. And a pure state of a quantum system is described by a normalized vector in this Hilbert space. And for vectors, I will always use this ket notation. And the bra is just the adjoint of this ket. And a mixed state of a quantum system is a probabilistic mixture of pure states, in the sense that you know, if you have an experiment and you prepare a system in a certain state, it's a pure state. But if you're not sure in which state the system was prepared, and you only know with certain probability it's in this state, with another probability it's in the other state, then this is mathematically a mixed state of the quantum system. And we can also describe this by positive semi-definite operators with unit trace. And what leads us to entanglement is now to look at composite quantum systems. So we have 2 quantum systems, maybe 2 atoms, and we want to look at the joint state describing the system. And what we do is that we take the individual Hilbert spaces that describe the individual systems, and we look at the tensor product of these Hilbert spaces mathematically. And now a pure state is called entangled if it cannot be written as a product state. So this is kind of the mathematical definition of entanglement. Eric before gave a more physical definition in terms of LLC operations, but I'm going to use this one. And probably the most important entangled state of, for example, 2 qubits is a so-called maximally entangled state. So imagine I take two, let's say 2 photons and I look at their polarizations, or I take 2 electrons and I look at their spins. Then a maximally entangled state would be one where I have a superposition of both systems having spin up and both systems having spin down. Okay, and then I normalize by this factor to get an actual normalized vector. And if I have a bipartite state describing a quantum system with 2 components, I can also look. I can look at the joint state, and I can also look at the marginal states in which the 2 individual systems will be. And in order to get the marginal state of a quantum system, I take the so-called partial trace, which just kind of discards the one system I'm not interested in and leaves the one that I am interested in. Mathematically, it's defined by this relation. So this means it's the adjoint of tensoring with the identity. And if I apply this to a bipartite state, I get the marginal state of one of the systems. And now you can convince yourself, or it's an easy calculation, that if you take the partial trace of this maximal entangled state, so you trace out one of these 2 systems, you will always end up in a completely mixed state. Which means that on one system, you have complete uncertainty about what state you will find the system in. And so now remember Charlie's quote from the beginning. An entangled state describes complete knowledge of the whole, which means the whole is in a pure state, in this state here. But I don't know anything about its parts, meaning if I take the partial trace over one of the systems, then the other system will be in a completely mixed state. And I have complete uncertainty about which state I will find it in. Okay, so this is a maximal entanglement. I will always denote these maximally entangled states by this phi plus. And there's a natural generalization to systems with more than 2 levels. So for example, so these would be qubits, and we can also talk about qubits, where you have an atom with d energy levels instead of just 2. But I will always use the same notation phi plus to denote maximal entangled states of these systems. Okay, so let's go to the main theme of this talk, which is teleportation. Let's first take another look at the standard teleportation protocol by Bennett et al. From '93. And so conceptually, the idea of teleportation is that you take entanglement between 2 parties that are spatially separated, and you give them a classical channel, which means that they can talk to each other on the phone. And teleportation now tells us that these 2 resources used together in the right way create a so-called quantum channel that let the 2 parties teleport a quantum state from Alice to Bob. So here, this is a pictorial description of this whole thing. So I have this entangled resource state on systems A1 and B1 between Alice and Bob, and the separation is somewhere here. I have the qubit that Alice wants to teleport to Bob in the system C. And then I have this classical channel, which, similar to Eric's talk, I will always, classical messages will always be noted by a double line to distinguish them from quantum messages. And the way that the original teleportation protocol now works is that Alice has these 2 systems in her lab, the system she wants to teleport, C, and the 1/2 of the entangled state, A1. And what she does is she performs a joint measurement on these 2 qubits that she has. And in more detail, what she does is she performs a Bell measurement. So for 2 qubits, there are 4 Bell states, which are the 4 maximally entangled states. And Alice just asks in which one of the 4 maximally entangled states are these 2 qubits. The measurement will yield a certain outcome, I. So for 2 qubits, this would be one of 4 messages. And she sends this message through the classical channel to Bob. And then based on this message that Bob receives, he applies a certain correction operation to his share of the entangled state, which after the protocol, if he uses the right correction operation, will then hold the teleported the states in which C was before the protocol will now be with Bob in the qubit B1. And this is an amazingly simple protocol. If you do the math, it takes you like 1 page to prove that this does the right thing. But it's still conceptually, it's an incredible discovery. And the good thing about this protocol is that it works exactly. So assuming that you have a perfectly maximally entangled state and that you have a perfect classical communication channel, this protocol will always teleport the exact state in C to Bob. But there's a disadvantage to this protocol, which is this correction operation that Bob needs to apply based on the classical message that he gets from Alice. And it means that the protocol cannot be used to implement arbitrary unitaries on a teleported state unless they commute. Okay. And port-based teleportation is now an attempt to turn this to get rid of this disadvantage. So what we want is we want a protocol that lets us implement arbitrary unitaries on the teleported state. But then we need to lose something in order to achieve this. So what we lose is that we get a protocol that is not exact anymore. It's just an approximate protocol, but we will see that this is not too bad. And the amazingly simple teleportation protocol is turned into something slightly more complicated. So we need a bit more machinery to talk about optimal protocols, and this I will do in the talk later on. Okay. So how does port-based teleportation work? We have again the same situation. Alice has some qubit in a system C that she wants to teleport to Bob. And they again share entanglement, but what we now assume is that they do not only share one maximally entangled pair of qubits, but they share n entangled pairs of qubits. So these are these n maximally entangled states here between systems AI and BI. A is always with Alice, B is always with Bob. And again, we have a classical communication channel between Alice and Bob. And the protocol has similar steps to the teleportation protocol. So Alice will again perform some joint measurement on all of her systems, which is now n+1 systems, the qubit C that she wants to teleport, and the n ports. So these are called port systems, A1 through AN that she has in her lab. She will then get a certain outcome from that measurement. She will send it to Bob, and then based on that message, and now the message is very simple. The measurement that Alice does just gives her as an answer one of the n ports, and she sends that label of the port to Bob, and then Bob just forgets all but the one port that the message labels. Okay, so he gets a number I, let's say 2, which tells him that the second port in B2 will hold the teleported qubit, and all the others he just discards. Okay, so mathematically what he does is he traces out everything but the ith port. Okay, so why would we want to make the initial teleportation protocol so complicated by introducing these additional ports? The reason is that we want to implement these unitaries, as I told you before. And the point here is that the correction that Bob has to do just consists of kind of picking up the right port and forgetting all the other ones. And so if you imagine that before starting the protocol, you actually apply a unitary to each port, then as a result, this protocol will actually teleport not the state psi, but the unitary u applied to the state psi. Okay, so the teleported state is processed by this unitary u, and the point is that I can here choose any arbitrary u that I want. Okay, and this really comes from the fact that the correction operation in port-based teleportation is so easy. It's not Bob doesn't need to apply anything to a qubit. It just needs to discard all the wrong ones and just keep the one port that holds the state. But there is a caveat to that. Processes or protocols that do this, that implement an arbitrary unitary on an unknown state, cannot be perfect with finite resources, which is a very famous no-go result by Nielsen and Chuang from the late 90s. And this is the reason why port-based teleportation cannot be an exact protocol, because it's forbidden by the laws of quantum mechanics in a sense. Okay, but we will see that you can turn port-based teleportation into a very good protocol as you add more and more ports, which makes it an asymptotically exact protocol, and this is enough for the applications. And speaking of applications, so we have we have a teleportation protocol now that is not exact, but it has this unitary covariance, and this enables a lot of applications of port-based teleportation. So one very important one is that it provides attacks on so-called position-based cryptography protocols. It can also be used to implement these universal programmable quantum processors, which is really that you apply an arbitrary unitary on a target state. And it can also be used in quantum channel discrimination. There's probably some kind of connection to entanglement-assisted quantum error correction, which colleagues and I are exploring right now a little bit. But the point is that all of these applications here do not work with the standard teleportation protocol because of the fact that you don't have this unitary covariance property, which port-based teleportation gives you. And since we don't have an exact protocol, we now need to come up with a way of deciding how good a protocol is. Okay, so somehow the goal is that we teleport this unknown, this qubit in an unknown state psi to Bob. So in a way, what we try to do is we try to approximate an identity channel from Alice to Bob, which I will call lambda in this talk. And then we need to now decide how noisy is this channel, or the other way around, how close is this channel to being perfect. And one very good way to measure this is to look at the entanglement fidelity of a channel, which is defined in the following sense. Let's say I want to teleport half of a maximally entangled state using this channel. Then I can ask how close is the output state to the original maximally entangled state. So here, this phi plus on the system C and C double prime is this here. Then I use the port-based teleportation protocol to teleport the C to Bob. And then I look how close is it to, again, the maximally entangled state. If the channel lambda is the identity channel, then it will just copy that one half of the maximally entangled state. And then the entanglement fidelity will be 1, which corresponds to a perfect channel. And the closer to 1 I am, the better the teleportation protocol is. Okay. And the inventors of port-based teleportation, Ishizaka and Hiroshima, had a fundamental insight that really significantly simplifies the analysis of port-based teleportation. And they realized that teleporting one half of a maximal entangled state through these ports using a port-based teleportation protocol is actually equivalent to a certain state discrimination problem. And the state discrimination problem is the following. So I have these n maximal entangled states between Alice and Bob. And then I look at the states that I get when I only keep one port on Bob's side and all the ports on Alice's side. So the first state would be all the A systems plus the first state of Bob, the first port system, sorry, which will be maximally entangled with Alice's first port. And then, for example, the third state in the state discrimination problem would be that the Bob's state is, Bob's system is maximally entangled with the third port in Alice's side. So I get these n states that I need to distinguish now, okay? And in a state discrimination problem, you usually have some probability distribution on the states, meaning that you kind of draw the state according to the distribution, and then you want to infer its identity. You want to say this is the second state in this problem. And here, for this connection between port-based teleportation to state discrimination, we assume that all of these states are drawn uniformly at random. So we have the uniform prior 1/n on all of these states. And then we have these n states, which I will call eta I, where eta I is the state where Bob's port is maximally entangled with the ith system on Alice's side. And then the equivalence is that the success probability in the state discrimination problem is directly proportional to the entanglement fidelity of the teleportation channel. The factor is this n number of ports over d squared, where d is the local dimension of the port systems. And I've here kind of depicted this equivalence in the case when you have maximally entangled states between Alice and Bob. There's actually a more general situation where you can have an arbitrary multipartite state between Alice and Bob, which does not have to be copies of maximally entangled states. And then this equivalence still holds in this more general situation. So this is really a fundamental equivalence between port-based teleportation and these state discrimination problems. And this is a very useful equivalence because state discrimination problems have a very nice description in terms of so-called semi-definite programming. So again, the task of state discrimination is you have a family of n states, eta 1 through eta n, each with a certain probability pi. It doesn't have to be uniform. So this is the general situation now. And you want to maximize the probability of successfully distinguishing these n states, which mathematically is just given by this expression here, where the pi are the probabilities with which you draw a certain state. The eta I is the state. Eta I's are the states, and then the ei here is the measurement that you use to discriminate the states. So this here is what I've written down here is the most general quantum measurement, which is a certain. It's called POVM, positive operator valued measure. Which means that you have a collection of measurement or effect operators, EI. They all need to be positive semi-definite. And you have one for each state. So in a way, each effect operator signifies that you have the ith state in front of you. And they need to be normalized in the sense that if you sum all of them up, then you get the identity, which means, so this is kind of like the fact that the probabilities all sum up to 1. And this is the so-called primal problem of state discrimination. And it's a so-called semi-definite program. And I will not go into the details of what this actually means, but from optimization theory, when you have a maximization problem and it belongs to a nice class, then you can form the so-called dual problem, which turns the maximization problem into a minimization problem. And state discrimination is one of these nice problems where you can do that. So the dual problem to state discrimination is just the following. You try to find an operator K that satisfies this relation here. So in the operator order, it needs to be greater than pi times the state eta I for each state. And what you then try to do is you try to minimize the trace of all such feasible operators K. And the nice thing about state discrimination in this formulation is that we have so-called strong duality, which means that the value of this dual problem is exactly equal to the value of the primal problem. So if I want to compute the success probability for a state discrimination problem, I might as well solve the dual problem, because I will, if I can do this exactly, I know that answer will also be the answer to the original problem. So mathematically, strong duality means that the success probability is equal in both cases. And so these problems have the same answer. So again, to kind of recap what we've done so far, we have this, we have port-based teleportation, which in which we want to teleport a state on Alice's side using a measurement to Bob. And we notice that it's equivalent to a certain state discrimination problem where I have these n states, eta 1 through eta n, with equal probability, and solving this state discrimination problem is equivalent to solving the port-based teleportation problem in a sense. And so now we can ask, how do we solve the state discrimination problem? What's a good ansatz for this POVM, for the measurement? And there is one pretty good choice, which is called the pretty good measurement. where you do the following. You define the average state of the state discrimination problem, which I'll always call eta bar. So it's just summing over all the states weighted by the probabilities. And then the measurement operators will be defined in terms of the inverse square root of this average state. So this is also the reason why the pretty good measurement is sometimes called the square root measurement. And what you do is you take the state you want to detect, the ith state, you weight it by its probability, and then you sandwich it by this eta bar, like the inverse of the square root of eta bar. Looks a bit peculiar, but it's easy to check that this is always a POVM. So the effect operators EI are always positive semi-definite. And when you sum them up, you might not get the full identity, but you always get kind of the projection onto the support of the average state. But that's fine because you can just restrict the Hilbert space to this support, it's called, and then it's just the identity on the smaller space. So in a way, everything outside of this support doesn't really matter in your problem, so you can just forget it. And the reason that this measurement is called a pretty good measurement is because it always does a pretty good job in a state discrimination problem. So this was the pretty good measurement was in this form first introduced by Hauslan and Wouters in the 90s. And then Barnum and Knill realized that in an arbitrary state discrimination problem, with a certain optimal success probability P opt, the success probability that you get when using the pretty good measurement is always at least as good as the square of the optimal probability. Okay, so you might not be at the full optimal success probability, but you're always close in a way. Okay, so you're always better than the square of this optimal probability. And the important thing now for port-based teleportation is that when you look at the protocol that you get from doing this pretty good measurement to solve the associated state discrimination problem, then Ishizaki and Hiroshima, and then later Beig and Koenig kind of did this in a kind of a clearer and more general way. What they showed is that when you use a pretty good measurement in the state discrimination problem, you always achieve a success probability that scales like d squared over n for large n and d fixed. And so since the entanglement fidelity of the port-based teleportation protocol is given by n over d squared times this probability, you actually see that it converges to 1 in the limit as n goes to infinity. And there's actually an explicit lower bound that tells you how fast this converges, okay? So just as a reminder, I told you before that we have this no-go theorem for port-based teleportation, which tells us that because of this unitary covariance property, the teleportation cannot be exact for finite resources, which at first is kind of a bummer because you have now a protocol that can't be perfect. But using this pretty good measurement and this result, it tells you now that you can make it arbitrarily good by just adding more and more ports. Yeah? Because as you take the number of ports to infinity, your entanglement fidelity approaches 1, which means that entanglement fidelity is 1 if and only if the channel is perfect. So the teleportation channel gets better and better as you increase the number of ports. And this is one way of showing that port-based teleportation even works in the asymptotic limit with kind of fidelity 1. But then it's also interesting to ask if the pretty good measurement is actually the optimal thing to do, because it kind of there was evidence that it is the optimal thing. And then one of the main results of this paper of mine is that the pretty good measurement is in fact the optimal measurement. So in a sense, for port-based teleportation, it's not just pretty good, it's kind of the perfect one. Like you can't do better than what the pretty good measurement does. Okay, to understand why it's the optimal measurement, we now need to talk about the symmetries of port-based teleportation. This might be a good place to stop and ask if there are any questions. If not, sorry, if not, I will just continue. So we want to talk now about the symmetries that we have in port-based teleportation, or equivalently in the state discrimination problem that I wrote down before. And one crucial aspect of this study is that the maximally entangled state, 5+, has a fundamental symmetry where you take any unitary U and you apply the unitary to one part and its complex conjugate to the other part of the maximally entangled state, and the state remains invariant under this operation. Okay, so this is a U bar symmetry of the maximally entangled state. And our states in the state discrimination problem are exactly made up of these maximally entangled states, 5+, between Bob's system and the ith port on Alice's side. And the rest is just maximally completely mixed states, right? Remember, the states I want to distinguish were parts of these maximally entangled states. And I told you in the beginning that the margin of a maximally entangled state is always completely mixed. And completely mixed states are proportional to the identity, so they have all symmetries, right? So this immediately tells you that I have this U bar, U star symmetry on the maximum entangled state, and I have the U symmetry on all the rest of the state. So this is the first symmetry that I've written down here. So in total, I have a U tensor N, which corresponds to the A systems, tensor U star symmetry, where the U star acts on Bob's system. But this is not the only symmetry I have. The other symmetry is that if I permute any of the n-1 remaining systems on Alice's side that are not entangled with Bob, nothing happens, right? So if I apply any permutation on the n-1 systems here, these are all just completely mixed states. So if I permute them, nothing happens. So I have a permutation invariance under the n-1 group, where S is the symmetric group. So this is the second line here. So for any permutation pi from the symmetric group on n-1 symbols, all of my states are invariant under those as well. So sorry, by the way, this notation here is just a commutator of two matrices. So this means commutator of A and B is AB minus BA. Okay. All right. So I have these symmetries on my individual states that I want to discriminate, these A to I states. But I also want to look at the average state, because this always also pops up in the state discrimination problem. And here I again have this U tensor U star symmetry, because the average state is just now a superposition of all of these A to I states, where the B is maximally entangled with one of the A systems. And the rest will always be completely mixed as before. So it's not hard to see that I again have this U tensor N tensor U star symmetry on the average state, because I have it in a way, I have it in each of these summands and it's linear. But what's more now is that I have again a permutation symmetry, but now I have permutation between all of Alice's systems. Yeah, so as a reminder, I will quickly go back to the previous slide. Before, I only had the permutation symmetry on the n-1 systems that are not entangled with Bob. But now for the average state, where I just like have a superposition of all of these states, so kind of like Bob's system will be entangled with everyone eventually, I can just permute them together and nothing happens, right? Because I have an equal superposition of all of these states. So now I have full permutation symmetry, where full now refers to the fact that I can permute all of Alice's systems. Okay, so I have these two kind of fundamental symmetries, one given by permutations and the other one given by unitaries. And so I want to quickly talk now about the representations of these groups. So the representation space that I will consider is n tensor copies of a d-dimensional Hilbert space. So this is the CD tensor n. And this space is a very natural space to study representations of the symmetric group and of the unitary group. because there are two very natural actions of these two groups on this representation space. And we've kind of seen them already. So first, the symmetric group on the tensor product just acts by permuting the tensor factors. So I've tried to write this down here in a kind of pictorial way. Mathematically, you define it on product vectors and then you extend it linearly in a straightforward way. So you have a product state, you permute it according to the permutation, and you get a new vector. Okay, and this is one action of by the symmetric group on this representation space. And the other action by the unitary group is also pretty simple. It's just applying that unitary to each space. So this is sometimes called the diagonal action. Again, this is kind of a pictorial way to describe this, but it's not very exciting because what you do is you just apply the same unitary to each tensor factor. Okay. But now what is exciting are two things. First of all, it's quite easy to see that these two representations commute with each other. So it doesn't matter whether you first permute the systems and then you apply the unitary at in each factor, or you first apply the unitary and then you permute the systems. So I think this is quite easy to see. What is a little less easy to see and not as trivial is that they not only commute, but they actually span each other's commutant. Commutant is just the set of all operators that commute with that set, okay, or group in this case. And the fact that these two groups, when you look at representations on this representation space, span each other's commutant means that you can decompose the representation space nicely into so-called irreducible representations. And this is called Schur-Weyl duality. To explain you how that works, I hope everyone has heard of the term irreducible representation before. An irreducible representation is a representation space that does not contain any non-trivial invariant subspaces. So just in a sense, you take some vector in the representation space, and if you act with the whole group on it, you will eventually get the whole space. This is an irreducible space. And it's been known for decades, if not centuries now, that the irreducible representations of the symmetric group and of the unitary group are kind of indexed or characterized by partitions of integers. So what is a partition? I have an integer n, and then a partition into d parts is a collection of integers mu1 through mu d, such that their sum is equal to n. And there's a nice pictorial representation of these partitions as so-called Young diagrams, where I take n boxes, and I form rows with these boxes, and the ith row has length mu I. So in this way, a partition naturally corresponds with these Young diagrams. So for example, if I take the integer 12 and I want to partition into 4 parts, I could take, for example, the partition 5, 3, 3, 1, and the corresponding Young diagram would be 12 boxes arranged in rows, with the first row having length 5, 3, 3, and 1. And you usually also require that in these Young diagrams or in these partitions, the row length cannot increase. Okay, so it can stay the same, like between row 2 and 3, but it cannot increase from one row to the other. And so now the irreps or irreducible representations of the symmetric group and the unitary group are indexed by these partitions. And for the symmetric group, there are so-called Specht modules, which I will denote by this W mu, where mu is the Young diagram. And we also know the dimensions of these modules or representation spaces, which I will denote by d mu. And on the other hand, the irreps of the unitary group, UD, are indexed by the so-called, are given by the so-called Weyl modules, V mu D, where I denote the dimension of these modules by M d mu. Okay. And Schur-Weyl duality now tells us that this representation space CD tensor n decomposes in terms of these irreducible representations. So we have a direct sum of where the index runs over the Young diagrams, mu. And then in each direct summand, I have a tensor product of the irrep for the unitary group, B mu D, and an irrep of the symmetric group, W mu. And the useful thing about this is that there's a very central result. It's actually very easy to prove, but it's very important in representation theory called Schur's lemma, which tells us that in this applied to this setting, this is not the most general statement of Schur's lemma, but applied in our setting, the way we use it is if I have a state on my representation space, CD tensor n, which just physically corresponds to n qubits, n atoms with d energy levels, for example. And if I have a joint state on these n qubits that is invariant under these two actions, so nothing happens if I permute the systems, and nothing happens if I apply the same unitary to each system, then I know that this state here is has a very easy form. It has to respect this direct sum structure that I get from Schur-Weyl decomposition. And furthermore, it's basically a completely mixed state in each of these summands. Okay, so it's in both, in each sector, it's proportional to the identity. And the proportionality, these R mu's are just the eigenvalues of the state. So they have to be non-negative, like the eigenvalues of any positive semidefinite operator. And they have to sum to 1 you have the dimensions here appearing too, because if you take the trace here, then you get the dimension here and the dimension here of these two representation spaces. So the normalization, the unit trace for the density operator translates into this normalization relation for these R mu coefficients. And this is a very technical detail, which I might actually just briefly say that in our situation, we have a particular symmetry, which is this U tensor N tensor U star symmetry. So we have n+1 systems, right? Alice's system and that wants to teleport, and the n port systems. And I have the full symmetries on the n port systems. So I have the permutation symmetry and the U symmetry, but then I have this additional system where I have this U star symmetry, okay? And then there's a thing called the Pierre rule, which lets you incorporate that symmetry into the Schur-Weyl decomposition, so that for the average state eta bar, similar to before, you get again this nice kind of block structure, where in each block the state is just a completely mixed state. But now there's actually a sum over two indices, but this is a detail that I don't think I want to go into too much. The point is just now that we can actually use these symmetries to try to solve this state discrimination problem. And the way we tried to solve it before, what I told you, is that we actually just choose this pretty good measurement. It's just an ansatz for a measurement, and we see what we get, and then later we show that it's actually optimal. And to see what we get, what we do is we take this relation for the success probability, which is given by the sum over all I of the probability of drawing the ith state, and then we have this probability here, which is kind of detecting this state. So the EI corresponds to measuring the ith state. And then if I insert for EI the pretty good measurement, which has this particular form here, then I have now this trace quantity of a product of eta bar type operators and these eta I operators. And from these symmetry considerations, both of these states have a very nice form, which is this block structure, where in each block I have a completely mixed state, and I can kind of compute these eigenvalues, which are the T here and the S mu alpha here. So I think I called this R before. This is the same as the R before. And doing that, you can actually get a very, nice compact description of the success probability in terms of representation theoretic data, which means that when I evaluate this quantity using these formulas here, I get a formula for the entanglement, for the success probability, sorry, where I have these dimensions of the irreducible representations appearing. So the md mu was the dimension for the unitary irrep, and the d mu is the dimension for the symmetric group irrep. And what I do is I have this sum over Young diagrams alpha on n-1 boxes, and then for each of these alphas, I have a Young diagram, and I now ask in what row can I add a box such that I still have a Young diagram, which means that the row lengths are not increasing, they can only decrease or stay the same. And then I evaluate for each of the rows where I can do that, I then evaluate this quantity, and summing over all possibilities gives me the success probability. And this is a result that was actually proved by in a very nice paper by Michael Leditzsky et al. And one of my goals in writing this paper was to really show that this expression here is actually the optimal expression. Okay. In a sense, because why do I say this? Because we said we make this ansatz of using the pretty good measurement to solve the state determination problem, but there's no way to know beforehand that this is actually the optimal thing to do. We only have this square root probability promise from the pretty good measurement. But it turns out that it's actually the optimal thing to do in this situation. And a nice way to prove the optimality is to use the STP duality that I showed you before. Right? So this state discrimination is a maximization problem, and using this duality, I can go to a minimization problem, where I minimize a certain quantity over all feasible operators k that satisfy this relation here. And if I now find a k for which the optimal value of this dual program is the same as the answer I got before, then I know that my answer from before is optimal, because the dual problem is an upper bound on the original problem. And you can do that, it turns out. So you can choose the k to be kind of like proportional to this operator that I was dealing with before, such that taking the trace is just the same answer as before. And then the optimality proof amounts to showing that this relation here is satisfied, which you can rewrite as saying that this average operator here with these weird eta bar powers is actually greater than the eta I, each of these individual states for each I. And if you can show that, then you really show that the pretty good measurement is optimal. And you can do that, and I won't go into details, but you can find those in the second paper that I wrote on the title slide. Okay, I have 12 minutes left, so I quickly want to talk about the asymptotics of port-based teleportation, which is the content of the first paper that I listed on the title page. And the goal here is to kind of get a feeling for these formulas that we could derive for the entanglement fidelity in terms of this representation of theoretic data. Because in theory, it's all nice. I mean, these are beautiful formulas, but it's a bit hard to see what happens when you take the n large. And I told you before, in port-based teleportation, what you want to do is you want to like add more and more ports, because you know then that in the end it will become an exact protocol. But somehow we now want to see how quickly does this happen and what's the optimal, what is this convergence, okay? So the asymptotic limit that we will always consider in this talk is that we keep the local dimension fixed, so the local dimension of each of these ports and the system you want to teleport. But it's fixed but arbitrary, so it doesn't have to be qubits, it can also be qubits. And then we take the n to infinity and we see what happens. And recall from before that we have this nice tool called Schur-Weyl duality, which tells us that our representation space, these n copies of a qubit space, have this nice decomposition in terms of these irreps for the unitary group and the symmetric group. And one thing you can do with this is that you can associate projections to these summands here. So for each Young diagram, for each mu, you have a projection. And then these projections naturally give rise to a probability distribution called the Schur-Weyl distribution, which is just the trace of these projectors divided by the total dimension of the system, which is d to the n, because we have n qubits here. And so the Schur-Weyl distribution, the values of this distribution for a Young diagram mu are given by these two dimensions of the irreps, the one for the unitary group and the one for the symmetric group. So the way I've tried to draw a picture here, where these boxes here are kind of the sectors in the sum here, and then they have different sizes depending on the two dimensions, and kind of this Schur-Weyl distribution corresponds to trying to measure in which of these sectors am I. Okay, and the larger the sector, the more likely you get this answer. Okay, and this corresponds in a sense to a problem called spectrum estimation, which is kind of the problem. You get many copies of a state, and you want to find a measurement for the spectrum of the state. And if you do this for the completely mixed state, you're kind of in the situation where you're doing this measurement here. You're kind of trying to measure which of these Young diagrams am I in right now. And so mathematically more rigorously formulated, if I have a random variable with values in the Young diagrams distributed according to the Schur-Weyl distribution. Okay, so this bold X is kind of like a random Young diagram, and the larger this sector is, the more likely it is. And if I now normalize this random variable by n, which is the number of boxes in the Young diagram, if I take the n to infinity, then this will converge in distribution to the flat spectrum. Okay, kind of like the square Young diagram where each row has the same length. Okay, so this is what, by spectrum estimation, what I meant before is this 1 over d here, this kind of flat Young diagram is just the spectrum of the completely mixed state, which is the flat spectrum. And kind of these randomly drawn Young diagrams behave in the asymptotic limit like the spectrum of this completely mixed state. The result actually holds more generally. If you take an arbitrary state and you do this, then you will get the spectrum of the state you started with. And you can kind of interpret this spectrum estimation result as kind of like a law of large numbers for Young diagrams. And then you can ask, what is the corresponding central limit theorem? What are somehow the fluctuations in this convergence here? And to do that, what we do is we take a random variable y, which is just the Young diagrams, so that we center them and we normalize them. We center them so that they have kind of kind of zero mean, and then we normalize them so that their standard deviation is normalized. And then the central limit theorem in this situation tells us, and this was proved by Johansson, that when I take the number of boxes to infinity again, that this random variable y, which are these centered and normalized Young diagrams, will converge in distribution to the spectrum of a certain matrix, which I draw from the traceless Gaussian unitary ensemble. Okay, since I don't want to go into details, I didn't write down the definition of these Gaussian unitary ensemble, but it's basically you can imagine it's a complex matrix that's Hermitian, in which the diagonal entries are independent real Gaussian variables, and the off-diagonal elements are independent complex valued Gaussian variables. Okay, I have a matrix and all of the entries are independent. On the diagonal, they're real Gaussian. On the off-diagonal, they're complex Gaussian, and it's Hermitian. That thing is a random object, it's a random matrix, and it's called, you can turn it into a traceless matrix, and then it's called the traceless Gaussian unitary ensemble. And the assertion of this central limit theorem is that the centered and normalized Young diagrams in the limit behave like the spectrum of these random matrices. But the caveat is somehow that this is the convergence in distribution. Okay, Okay, so in probability theory, there are different notions of convergence, and this is a particular one where the random variable converges in distribution, which means that the cumulative distribution functions converge. And to apply this to our case, remember that the expression of the entanglement fidelity that we want to understand is given in terms of these sums over dimensions of the Young diagram, of dimensions of the irreducible representations indexed by these Young diagrams. And the idea is now to rewrite this fidelity as an expectation value over Young diagrams. Okay, so where the probability distribution is the Schur-Weyl distribution that I wrote down before. And then the idea is that we want to use the central limit theorem to compute this expectation value in the limit where we can replace these Young diagrams with the spectrum of these Gaussian unitary ensemble matrices. And that's much easier to compute, okay? Because it's just D by D matrices with normal entries, and it's just easier to do computation with this. The problem is that the central limit theorem in the form that we knew before our paper was just convergence in distribution. And here we need a stronger convergence, which is convergence in expectation. So we need that the expectation values of these functions actually also converge. And so in our paper, we proved this for suitable functions f that include all of the functions you get from these rewritings here. And then it allowed us to really, in these expectation value formulas, replace the Young diagrams with the Gaussian unitary ensemble matrices. And then we can actually compute the asymptotic behavior of the entanglement fidelity. And for example, for the entanglement fidelity of porpoise teleportation in the form that I explained it to you, we get that asymptotically for fixed d and sufficiently large n, it has this formula where the kind of like the first order correction is this d squared minus 1 over 4 times 1 over n. And then you have some other stuff that's decays faster. And an easy consequence of this is the known result from before, that if you take the n to infinity, the fidelity really goes to 1. So asymptotically, the protocol becomes perfect. But now you actually know pretty well for large n how the convergence is taking place. Okay. This brings me to the end, and I'm also already running a little bit out of time. So I will just briefly say, I talked about a very specific family of porpoise teleportation protocols, or kind of like a specific protocol where these port states are just n maximal entangled states. These are always these like squiggly lines that I wrote. You can look at much more general protocols where you have just some arbitrary multiportite state between Alice and Bob. For example, you know, they could try to share these entangled states, but then there's some noise when they do this, so they have something else. And the question is now, what happens? Can I still use the same techniques? Can I still use the same symmetry considerations in this more general situation? And the answer is yes, because it turns out that you can always symmetrize this port state in order to enforce the symmetries that I talked about. And kind of like the thing that you need to prove is that when you do this, whatever protocol you get afterwards is at least as good as the one you started with. And that's what Christian Mayans, one of my co-authors, did in his PhD thesis. And then we, in the first paper that I cited before, we kind of like put this on more general footing. And it turns out that then you can also analyze the asymptotics of porpoise teleportation. You can also derive these representation theoretic formulas, which was done by Michal Leditzsky and his co-authors. And it actually turns out that this is better than the one that I showed you, because the first order correction is not 1 over n, it's 1 over n squared. So the convergence to 1 is faster. Okay, so now I really have to conclude because I'm actually out of time. So just quickly, porpoise teleportation, it's an approximate teleportation scheme with a very nice property called unitary covariance that gives you all kinds of interesting applications. It has a lot of natural symmetries that I hope I could convince you of. that allowed us to characterize port-based teleportation in terms of representation theoretic data. We can use tools from representation theory to do this, like Schur-Weyl duality. In order to determine the asymptotics of port-based teleportation, we could exploit an interesting connection between representation theory and random matrix theory. There was these GOE matrices, the Gaussian unitary ensemble matrices. And we developed a lot of machinery for this tool to bring kind of random matrix theory in. And an open question is what other quantum information theoretic tasks with similar symmetries allow us to analyze the asymptotic behavior using these tools that we developed or improved. Yeah, thanks for your attention.